So we do the solution now of exercise 6, the design of an off-grid system with an inverter. Just a repetition, we discussed the questions about a tropical solar home system which has the following electricity needs. We have a ventilator with a power of 60 watts that operates from 9:30 until 11 p.m. We have 5 conventional light bulbs at 60 watts each, operating from 7 p.m. until 11 p.m. There it's considered that we should think about energy saving option. So as an engineer, you should not only think about the give values, you can also think that you modify, for example, some loads in order to make the whole system more economic. We have a notebook computer of 30 watts that operates from 6 p.m. to 9 p.m. We have a TV set of 100 watts operating from 8 p.m. to 10:30 p.m. If you take a look at these numbers, at these values of the consumption, and see that it's not a lot of room for improvement for the notebook and the TV set. What we should do is to calculate the load, respectively the daily consumption to be supplied, considering the energy saving options, and then we calculate the battery size for a system voltage of 24 volts. The battery cycle efficiency of the round trip from charging to discharging is 80%. Then we have the efficiency of the charge controller which is 0.95, and the inverter efficiency is 90%. And we calculate the panel size. We have a conversion efficiency under standard test conditions. Just quite low temperature of 25 degrees, while we are in the tropics. Temperatures at the module are quite elevated. Therefore, we have a relatively low performance ratio of only 0.8. If we calculate the panel size, we have also to consider the irradiance. While the system has to work through the whole year, we take the typical irradiance typical daily irradiance during the first month of the year. And for Rio, that's 4 kilowatt hours per square meter per day. While if you compare it to Germany, we have in good locations 1 kilowatt hour per square meter per day. In really bad locations, we only have half a kilowatt hour per square meter per day. Then we have to calculate the cost of such a systems. First, the investments cost, the initial costs, the big K, and then the specific costs, small k, during 20 years. We calculate with the irradiance, which you receive there 1,800 kilowatt hours per square meter per year. We consider PV panel at €1 per watt. That's relatively expensive, but you have to consider local market prices. That includes duties and so on. So that's a realistic value. And a lifetime of 25 years. So during 20 years is 25 years. We have to exchange that. Opposite to the battery, which has a lifetime of 4 years only. That's also due to the elevated temperatures there. We have to exchange the battery relatively often. And the mounting support structure, which is also a scheduled lifetime for 25 years, we calculate with €0.5 per watt peak. We have to consider the energy saving measures. So it's a very good idea to substitute the 60 watt antique light bulbs by LED bulbs. 8 watts is already not really the latest generation, but quite easy to reach 8 watt each. So we have instead of 60 watts, we have 8 watts. If you multiply it by 5, because we have 5 light bulbs and the duration of use 4 hours, we have instead of 1,200 watt hours per day or 1 or 2 kilowatt hours, we have only 160 watt hours. That means we saved 86.6%. The plan how to design a system is included in the lecture. So first we determine the load. So we take the power of each load and its duration of use. So we have the end time of use minus the start time of use, and add these up from load 1 to load n if you have n different loads. And if you have an inverter, we have to consider the inverter efficiency also. Then we determine the battery size. So we have here the maximum applied depth of discharge, which is typical for at least acid battery of 0.5. I'll show you a graph later on that. If you use lithium-ion batteries, they are more expensive, but you can discharge them to a much larger extent, not fully, because lifetime is also reduced there. And the days of autonomy, so how often do you expect there is an equivalent day without any irradiance? That never happens, but you take this as an equivalent, and in the tropics you take 2 days, while in Germany there could be long weather periods, little irradiance for a week or so, and that is equal to 4 days without irradiance. And for the tropics it's enough to take 2 days of autonomy. So we have here the energy to be stored in the battery. That's energy needed by the load multiplied by the days of autonomy, because you have to store for several days, and the maximum divided by the maximum depth of discharge. The energy to be generated by photovoltaics, as I mentioned, we have to use energy methods before. It makes complete sense. And then we have to consider also the efficiency of the battery, but also the electronics. That's here the charge controller. Then we take the daily irradiance at a typical day in the worst month of operation. So usually the worst month of the year, but maybe if you have irrigation and use it for agriculture, you don't have to consider all year, but the times when you use that system. So for us it's all year, and you can do it via measurements or tables or simulation and so on, and call it red day. That was given already in our example with 4 kilowatt hours per square meter per day. Then you can calculate the area of the PV generator. This is the energy to be supplied by the PV generator divided by the irradiance of the day times the conversion efficiency under standard test conditions times the performance ratio. You can also calculate the nominal power of a PV, because usually you don't buy PV not by area but by nominal power under standard test conditions. So that's the area times the irradiance under standard test conditions. You all know that it's 1000 watt per square meter times efficiency. Can simplify that, so we eliminate the conversion efficiency. So even if you don't know that, you can calculate that. Now you have the energy to be generated by photovoltaics from here times the irradiance under standard test conditions, that is 1000 watt per square meter, times the irradiance of a day in the worst month of the year times the performance ratio. Let's do that. So just again the repetition of that. So we just start with the load consumption. So we have one ventilator and it operates for 13.5 hours, and gives a load of energy be supplied during a day of 810 watt hours. Then we come to the LEDs, not the light bulbs anymore. We substitute them. They consume 8 watts only, 4 hours, and we have a consumption of 160 watt hours per day. Then we come to the notebook, 30 watts times 3 hours and 90 watt hours for a day. And the TV operating for 2.5 hours, 100 watt, 250 watt hours. Altogether here, added up here, we have to build the sum here. That is 1310 watt hours consumption. Sometimes for the inverter you have to know the maximal power. So if all appliances are switched on at the same time, we have a maximum power of 198 watts. So the maximum power of our inverter could be 200 watt or so. This is a small star. That means we did consider the inverter efficiency. We calculate this also. So we have here the load, and we have to consider the inverter. So this was our load we calculated, include the inverter. Then the next calculate the battery, and as a last step we calculate the size of the PV panel. So the battery cycle efficiency take as 80%, the efficiency of the charge controller 95%, and the inverter efficiency, which we include now, is 0.9. And if you include that, so here we divide that value W star load divided by the inverter efficiency. We have the actual load we have to consider, and that is 1455.56 watt hours that we have to supply by our PV panel. I mentioned already, if we calculate the depth of discharge, I show you this graphs, how much the graphs depend on the how much the lifetime depends on the depth of discharge for two different types of battery. We have the consumer battery, often car batteries and so on. And if you see, if you discharge them very deeply, lifetime is very short. So this would mean for your application that's less than a year. If you have industrial battery, they are more expensive, about double as expensive as consumer battery. But as you see, lifetime is much longer. Even if you discharge them by 90%, it's about 800 cycles. But good compromises that you take 50% of depth of discharge, then a lifetime is about 1,800 cycles. You can even prolong this lifetime if you, for example, only discharge it by 30%, then a life cycle could come up to well, almost 4,000 cycles. This depends on a lot of parameters, on the brand of your battery, but also on temperature. Temperature has a vast influence. Rule over the thumb is if you increase the temperature of the battery by 10 degrees, lifetime is only half. But we come to this a bit later when we come to the chapter energy storage. So first here we take here 50% depth of discharge, and we arrive here at 1,900, 1,800, 1,900 cycles. These are full cycles. We don't need the full cycle for every day. So lifetime is a bit longer, as I told. It's a bit calculated about 10 years, which would equal about 3,600 cycles and so on. So we calculate the battery size now. We only take depth of discharge and 2 days of autonomy. We don't need all the time this depth of autonomy, but for really bad day we have to consider that 2 days of days of economy. So here we have our load times the days of autonomy, 2 days, depth of discharge divided by 0.5. Altogether we have to store the theoretical maximum capacity is 5.8 kilowatt hours. Usually you don't buy by kilowatt hour battery, so you have a certain voltage and buy it by ampere hours. So that's called a C, a battery capacity. So in terms of ampere hours, so you have the energy to be stored in the battery divided by the voltage of that battery. We have 24 volts, and so we arrive at a 242.59 ampere hours. So that's quite uncommon. So usually you have a size of a battery of 250 ampere hours. So the actual battery size is a bit bigger, so it's about 6 kilowatt hours. This is also good for the lifetime, and also we have to considering manufacturing tolerances, as we found out when we measured some battery sizes. So it's never that accurate that you really have the capacity given on the number plate. So we calculate now the panel size. We have the conversion efficiency of 16%, performance ratio of 0.8. Then we have here the load of the PV panel divided by the efficiency of the charge controllers, and divided also by the efficiency of the battery. So we have to supply by photovoltaics 1.9 kilowatt hours per day. This number derived from here, so don't have to consider the battery, days of autonomy and so on. We just have to consider really the energy to be generated. So we have for the area of the PV generator, we use a formula, so you put that in. So the energy to be supplied is 1.915 kilowatt hours per day. Then we have the irradiance for worst month of the year, and the daily irradiance is 4 kilowatt hour, 4,000 watt hours, times the performance ratio times the efficiency under standard test conditions. So you arrive, just check also, it's always a good advice to check the units here. So divided gets, the day gets eliminated, and kilowatt hour gets eliminated here, and so we arrive at oh sorry, it's not watt hours, it's watt hours. This is wrong here. Kilo must eliminate it here. So we have a size of 3.74 square meter. The nominal power is then, if you put in the number, 5, the size area times the irradiance under standard test conditions times the conversion efficiency under standard test conditions, because it's actually the power under standard test conditions, and that is very close to 600 watts. The actual area size is then a bit bigger than we calculated, because we can't, usually that's the next size. It's very close to that at 3.75 square meters. So let's come, can also calculate it directly. So PST is just this, so we don't have to consider the conversion efficiency by that. So we are now calculating the costs, the initial investment costs, and the specific costs during 20 years. This have been the values given here for the location, and the total costs are the costs of the specific cost of the PV panel, calculated. This is €1 per watt. In a factory in China you may get from 0.3 watt peak, but there are margins, there are customs and so on to pay and so on, so that's expensive. Same for the batteries, and here local produce balance of system costs, that means installation and substructure and so on. So we just put in the numbers here, €1 for the PV panel plus 0.5 for the support structure is 1.5 euro per watt times 600 watt nominal power under standard test conditions. Then we have the battery cost is 300 euro per kilowatt hour. We have 6 kilowatt hour. Altogether we arrive at 2,700 euro initial price. So we don't have to care during this 20 years about PV balance of systems costs, but the battery have to be exchanged after year 4, after year 8, after year 12, after year 16, and we have to, while we consider 20 years only, we don't have to exchange it anymore in the year 20, because the financial horizon is limited there after 20 years, so we just finish at year 20. So if we see, add this up, so we have the cost for 20 years, so that's the cost of the PV, it lasts for 20 years. We have 5 times the cost of the battery, so initial costs plus 4 exchanges, and the cost of our balance of systems. So if we add this up, so this is the same. The PV generator initial cost is the cost also for 20 years, also for the balance of system costs. So we have €1 for the PV panel plus 0.5 euro for the BOS. So we have 1.5 euro per watt altogether times 600 watt standard test conditions. 5 times the battery costs, 300 euro per kilowatt hour times 6 kilowatt hours, and we have then 900 euros plus 5,400 euros is equivalent. This is 6,300 euro. What you clearly see that the cost of the PV generator is quite low. The main costs are the batteries. So if you do all cost optimization, you should think about how to make the batteries cheaper, not so much really about how to make the photovoltaic generator cheaper. These are the investments cost during 20 years. Let's take a look at the specific costs. So first issue is if you calculate that for a yearly irradiance of 1800 kilowatt hour per square meter per year. So that means how much worth is our PV electricity also being stored. As the next step, we would all take into consideration how much is it from the load perspective, how much does each kilowatt hour of the consumed energy at the existing load costs. But let's start first, as mentioned in the exercise. We calculate that for a yearly irradiance of 1800 kilowatt hours per square meter, so that's a bit more than the worst month equivalent. So we will have some surplus in doing the year, so we can attach additional loads. For example, in summer we can attach air conditioning or something like that, or use the ventilator for a longer time period. So this is what I said. The daily PV production is calculated for the worst month of the year. In summer we have more. So now we calculate the energy being generated during the whole year or even for 20 years. So we have this year 20 years times the irradiance 1800 kilowatt hours per square meter per year of irradiance. That is our area of our PV generator. That's the conversion efficiency under standard test conditions, and that's the performance ratio considering the elevated temperature and non-particular incidents and so on, so it's the non-STC conditions. And altogether we have 17.28 megawatt hours. The specific energy costs, so that this is the investments cost during 20 years divided by the energy being generated during that 20 years, and that's 1,300 euro divided by 1,280 kilowatt hours, and so we arrive here at 36.5 euro cent per kilowatt hour. So that's definitely more than even in Germany we pay for grid electricity. But as you saw, the main costs are not from the PV generator, it's from the this is from the battery. As a comparison, now we consider for the given loads, so even a bit worst. So there will be wasted energy during summer, and we just consider the energy consumed by the existing loads given in that exercise. So the electricity generation after doing 20 years is more, but now consider the load only being consumed. So we have the daily load here, so remember 1455.56 watt hours per day. And then we have 20 years, and we have 365.25. That's the actual number of days. If you have 20 years, we can really use that thing, considering also the shift years and so on. And so this is 265.25 days per year. So days gets eliminated, years get eliminated, and here we have watt hour per day. The day gets eliminated, so we have here the rest watt hours, or exactly 10,633 kilowatt hours of energy being produced, of electric energy being consumed, sorry, with loads during that 20 years. And this we have the investments costs and the load during 20 years, and that is our result. So we have, considering the existing loads, we have 59.2 euro cents per kilowatt hour. So that's almost double as expensive as electricity from the grid in Germany. Thank you very much.